Hello, welcome to Lab 3 for Physics 2, the magnetic field of a permanent dipole. The purpose of this lab is to visualize how a magnetic dipole looks in 3D space in three ways. Those three ways are computational, experimental, and theoretical. A secondary purpose of this lab was to prove the inverse relationship that the strength of a magnetic dipole has with distance. Some models and principles used in this lab. The first equation you see is the Biot-Savart law for a theoretical dipole, which was given to us in the lab instructions. The second equation you see is how we analyzed our data to describe the relationship that magnetic dipole strength has with distance. A preview of my main result, my n was about -3, and the magnetic dipole, mu, was 2.5 amps per meter squared. So from the select all that apply on the experiment instructions, the two observations that I noticed were that when the magnetometer is far away from the magnet, it measures a near zero field in the x direction, and then as it moves closer, the measured x component of the magnetic field increases. This makes sense because as the magnet gets closer, its strength will become greater. This is how we conducted the experiment. Initially, the phone app we used was adjusted in a direction to eliminate the X component of Earth's magnetic field. This was so that we can measure only how the bar magnet was acting on the phone. Next, we found the exact location of the chip on our phone and labeled it with tape. So there were two parts to the experiment. Part one was finding the X component distance from the magnet, which was on axis, and then we linearized our data to find n. And then the second part was measuring the off-axis magnetic field of the dipole. And to do that, we used the perpendicular distances at a certain strength of the magnetic dipole. And then this would give us the magnetic field. This is my data. On the left is my data from the on-axis dipole measurements. And then we took that data on the left and linearized it to create the graph on the right, which is the natural log of the magnetic field in the x direction versus the natural log of the distance. And then this is how we got our n, which is -3. This data was for my off-axis measurements, and the top red circle number is the distance d, which I used in my coding section to get the 45-degree angle magnetic field. And then on the bottom, the three numbers circled in red are the x, y, and z component of the magnetic dipole we measured during the off-axis section of the data. So in order to get my data into numbers, the slope from the linearized graph on the last slide was -3, and therefore my value for n was -3. My value for k using the formula was 5e -7, and then I used the equation for the magnetic field to find the magnetic dipole moment, which is 2.5 amps per meter squared. This is my code that I used, and the top left is a function that is allowing vectors to be turned into arrows to represent magnetic fields at different locations. And then in the bottom left are 6 arrows that I created, 2 arrows on axis, 4 arrows off axis to represent the magnetic field at all those locations. And then on the right side of the screen were just the rest of the lines. And then this is the section of code where I created my 45-degree magnetic field observation. And this is my result. So as you can see, the green arrows are pointing in direction of the off-axis field. That's because they are perpendicular to the magnetic field of the magnetic dipole. My orange arrows are on field, and then my purple arrow is pointed at the 45-degree angle. And then the comparison from my computational to my experimental, the distances I found were about 3% different, which is very similar. And then the magnetic fields were very not similar, as you can see by the comparison between the two vectors here. So for the first what if question, if I hadn't ordered my phone with respect to the Earth's x coordinate, then the dipole from the Earth would have caused the data to be skewed in the x direction that my phone was favoring. And then for the second what if question, if I were to stick two identical magnets together, then if I ran the experiment again, our measurements would have approximately been double their values in the experiment we just ran in this one. But the net direction would still remain the same because the two magnets act in the same direction. Thank you.